Good morning, everybody, and welcome to the second hands-on session of Quantum GIS. First, you please open the QGIS interface, and I hope that you have saved the last project we were working on. We will start from same project, and today we will learn about some more about symbologies. Then how we can introduce scale dependent visibility of the feature in a map. And then we will learn about the classification of the data, means the different features in a single vector layer, how we can classify it. Okay, means giving different symbols and different color of different entity in a single vector layer, how we can do that. And then we will learn about the projection system in GIS. What is GCS, what is PCS, how we can convert from GCS to PCS, and also if you have data in one of reference system, then how you can convert data from one reference system to another reference system. That we will learn today. So this may be 40 and 50 minutes lecture. I hope you will enjoy it. So I request you open that project we were working on. This one, the project we were working on. So this project is actually Jurala irrigation projects. It's data about the Jurala irrigation project, and that vector data was created using remote sensing image. That image was procured by NRC, from NRC, and currently we have 12 layers of that project, and this 12 layers consist of various layer of structure, settlement points, railway tracks, roads, streams, reservoir, river, and study area. And you can see currently we have enabled level for settlement point layers and that reservoir layer. Okay, now we will learn the feature about the orientation of the label, how we can change the orientation of the label, and we required some time to change the orientation. For example, in case of river, you see, first I will enable the label for river. This is my Krishna river. So you know how we can enable the label. Just go to the property, label, and single label, and this is the attribute table column. I think you can see, if you open its attribute table, there is a column river name, and under this column the name was created or entered by the user. We will use this column to label our vector layer. So this consists 6 and I think 7 features. These are tributaries, and this is the main river. Okay, one island is also there in the river, small island. So we will use this column. Okay, we can also directly use this button also, that is shortcut button or label. You select first layer, river layer, and then label, and this is the column that contain the name. Okay, assign it and apply it. You will see the Krishna river now come. Now the orientation of this is not appropriate, means it should come along the river. So how we can change the orientation of this Krishna river label? Again, you open the property table and see here 7 or 8 tabs is there, and under this tab, placement tab, you will see 6 options of placements. So use this using parameter curve and apply it, and you see now Krishna river label's orientation has changed. I think this is the orientation we want, and it changes for every, means it's every features, like it's a tributary and this is a small island in the river. Okay, so that is how we can change the orientation of the level. You can experiment on that others, other options. The total 6 options was there. Okay, next thing is about how we can introduce scale-based visibility to our map. Now, what is scale-based visibility means? I think if you have opened Google Map in your mobile and if you try to search any mall or shop, but initially it will not visible in your map. Once you zoom that map, after a particular scale, that particular entity you will see in the map. So that is called scale-based visibility. Means you want that my features should appear in the map after it reaches a particular scale. Okay. In our current project, you can see structures layer, that is red square, they are overlapping each other. Means its appearance is not good. For the current scale, that is 1 raised to around 4 lakh, 1 by 4 lakh, you see these are overlapping to each other. And if I will take the printout of this map, then any good expert of map will say that your map is not. So what you do, you introduce a scale-based visibility to your map. Means I want to see this feature only a particular scale. Now, how to introduce this scale, this feature, then you know better what actually I am describing here. Okay, so first I will, the steps are, first select that layer and property, and then you will see rendering option. Okay, in last rendering operation, you just enable this scale dependent visibility, and your scale, minimum scale, you want to enable this. Okay, so currently I want that this particular is around 1 lakh, 1 raised to 1 lakh. Apply it, and you see that now that all feature has gone, because my scale is 1 to 2 lakh 90,000, but I have given 1 to 1 lakh. So if I increase my scale of this map, you see now features appear, and scale is this. Means if my scale is greater than 1 to 1 lakh, the feature will appear in the map. But as soon as you reduce your scale map to less than 1 to 1 lakh, that feature will disappear from the map. Okay, that is called scale-based visibility of the feature. And it is important because first it's improve the visibility of your map. Also, during printout of that map, means if you want to export this map in PDF and then print that map, it will control which feature you want to show in a particular scale of map. Means if you want to take a print out in A4 size, then if you try to show this structure features in that map will become, means this feature become overwhelming in the whole map. But if you take this map in an A0 size paper, then maybe the scale, that is 1 to 1 lakh, it's suitable for A0 size, and that feature will appear in that map. So you are making actually a dynamic map, and you are controlling which feature should appear on which scale and which feature should not be appear on which scale. So that is how you can make a dynamic map. Okay. Similarly, you can introduce this feature in a label also. Currently, the labels you see, they are very overwhelming to that whole map of the command area. So what we can do, we introduce same, that is 1 raised to 1 lakh, means this scale, this particular label should come if my scale is greater than 1 to 1 lakh. Okay. So how to introduce this feature in labels? Same, you open that property. So that layer is settlement point, which okay, and then open the property and labels. Again, you see rendering option here. Okay, this rendering tab, you enable this scale dependent visibility and put 1 lakh here. Okay, and apply it. Now that whole label has now gone because my scale is less than 1 to 1 lakh. So if I increase my scale greater than 1 to 1 lakh, then these all labels will appear in that. So that is actually scale based visibility and how we can introduce. I hope you learned the steps, and it is actually important. That is why I thought that it should be told to you. Next thing, we will learn about the classification of data. So what classification of data means? See, in our structure layer, you will see red square. These layer contain the location of the structures along the network, canal network. Structures means aqueducts, bridges, okay, superstructures. So these are the location of the structures. But currently we are using a single symbol to describe all the structures. So when you take the printout and give listen, then maybe the user of that, maybe the person who want to see the map will confuse, means where is that aqueduct and where is the bridges. Okay, so you want that a proper symbol and proper color in a single vector layer. So what we have learned today, so how we can actually do this. So this is called classification. Classification means introducing different symbols and different color of various entity in a single layer, single vector layer. Okay, in GIS typically we use 3 type of classification. One is unique value classification, second is graduated classification, and third is rule based classification. Other option is also there, but these 3 are most important and generally used. What is unique value classification means? If your layer contain features which have a unique value, for example structures, if you try to open the attribute table of this structure, you will see we have here structure code for that layer. Structure code means user have used code to define the structures. One means it's a aqueduct, 2 means it's a bridges. So like that he has created this attribute data. So each different feature contain a unique value, and once you use this value to classify the data in a layer, that is called unique value classification. So how we can do unique value classification? First you select that layer, okay, open its property and then symbology, and you change this single symbol to categorize, okay, and value means you should have give the column name which contains the unique value. So structure code contain the unique values, you assign that column, and symbol is, we will use same symbol, and now classify it. Now different value have different color, okay. So that is how you can change the colors of various entity in a single layer. You apply it. Currently you not able to see because we have enabled that scale based visibility. So you zoom it, and now you see these colors has come, okay. Further you can also change the symbols for individually, you can change the symbol also. Same, open the property table and you can change the symbols also. So for one we will use this symbol maybe, okay, change the size. Then for 3 we can use square, okay, we can use this, okay. Similarly you can also apply others symbols. So you see the symbols also change and also color. So that is how we can classify different entities in a single layer, and now it is helpful for creating legends in our output map, okay. Now we will learn about graduated symbol and or graduated classification and where it is applied, okay. Now this is unique value which we have learned, and the graduated is nothing but actually your data or your features value in a layer have some range, means it's have a minimum value and maximum value. For example, if you have a vector data of contour map and your contour value is changing from 100 to 1000 meter, and you want to show the map, means you want to show the contour in the map like that, 100 to 200 the color should be red, 200 to 300 color should be yellow. So you are giving an interval, and in that interval the color will be different. So that is actually called graduated, means you are giving a particular interval to your data values, okay. It's not a unique value but a interval. So how we can introduce this graduated classification to a particular vector layer? So we will use this reservoir layer, okay, to introduce this feature. So reservoir, if you open that attribute table, you will see a one column that is area. It's actually area of the reservoir in meter square, and this is in kilometer square. So we will use this column, and its minimum value is about this and maximum value is this, and we want that more area reservoir should appear in a darker color and less area reservoir should come in a lighter color, okay. And we will give interval from this to this. So we can control the interval, maybe 6 classes or 7 classes. Okay, so how we can do this? The steps are: first select the layer, open its property table, okay, dialog box, that is property dialog box, and then symbology, and you change to graduated, not category, graduated. This is used for unique value and this is for graduated. Okay, and that column name which contain the values. Okay, my area, and we will give color ramp. Color ramp means the minimum color value and maximum color value. So light color, light blue color. Okay, and dark blue color we can give. Okay, and then classify it. So you see, currently we have 5 classes. So areas minimum value and maximum value, we have given interval of 5 classes, and this is the colors of each interval, and we apply it, and okay. Now this is called graduated symbol. If you full zoom your map, you can see higher area have darker color and very less area this is have lighter color. Okay, and this is also, you see, very light color. So this is called graduated classification. Same steps you can apply for a contour map also. A contour map have a range, so you divide your range into different 5 or 6 interval, and you can give different colors to the different. Currently we have used only single color ramp, so you can also use a different color ramp or a random color ramp. You can also use that, and you can classify your data in a map. Okay, now why it is important? Because it's first, it's helpful while making legends. Second, it's also helpful to distinguish the features from other features, and also it your map become more informative. For example, in contour map, you can very well define low lying area and high lying area and middle lying area by showing the different colors. Okay, so this is graduated classification. Okay, now we will see next feature of the GIS, or you can say quantum GIS, is about how we can calculate the area or length of the feature. And I think it is a must person, any GIS user should know how we can calculate the area and length or other parameters of a GIS map. So GIS is not only to produce map, but also you can do some analysis. Means you can calculate the area, length. Okay, you can overlay one map to another map, and you can also create some information from overlapping of two layer or two maps. Okay, so now we will learn how we can calculate the area. I think you have seen this reservoir, and there is a column is my area, and here the area has been calculated. Okay, now you should know first this thing, that if you use ArcGIS, then if you will digitize any data and you create a vector data, So ArcGIS will automatically calculate the area. But in QGIS, you have to calculate manually. Every time if you change the feature or you modify it, every time you have to recalculate it. Then only you will see the latest area of that particular feature in the map. In QGIS, please remember, you have to update the value if you change the feature in a particular layer or modify it. Now, how to calculate? See, area and length. First, you should know that your map should be appropriate. Means it should have a proper datum and projection system. If your data is projected in a wrong coordinate system, you will not get proper value of the area and length. Very first thing you should know. Very important. Now, before I proceed this exercise, how to convert length and area, first you know what is the projection system, what is GCS, PCS, how we can convert data from one reference system to another reference system. So I will use my 10 or 12 page PPT to describe it. So right now I will minimize this QGIS interface and I will open my PPT. Okay, and now map projection. What is map projection? So this, what is this actually? It is a geographical coordinate system. I think everybody knows. Here data or any point on earth is represented by longitude and latitude information. Okay, and Z is the height from the MSL value. So this is your GCS system, means we are working in a degrees. So any point in your map, it is, for example, for this point, the latitude is 10 degree and longitude is around 20 degree. So this point is called, what is, how we can define this point? It is, we can define like that, 20 east and 10 north value and 20. Okay, so E20 and N10, I think. Okay, so this is how we can denote a point on earth in form of longitude and latitude. So this one is longitudinal value changing and this one is your latitude value changes, and this is the angle is calculated from the Greenwich Mediterranean. Okay, and for latitude it is 0 is for equator. Everybody know, I think. Now I will take a small exercise. What is the length of 1 degree increment on a meridian and on a parallel at 30 north and 90 west? This is the point location, 30 north and 90 west. If we go 1 degree increment, how much length we actually cover on a meridian and a parallel? So I think this mathematics everybody know. In a GCS system, if we go along this A to B, the length is your radius of earth and your latitude angle difference, okay, from A to B. And length on a parallel, this is called parallel, is calculated. First you have to calculate your radius r, and that is actually r cos phi. Phi means the latitude. So you calculate the r and then you multiply with this angle, that is longitudinal change. Okay, and you have this formula series re delta lambda cos phi. So that is how we can calculate the length if in a on a parallel and median. So we have used the same formula here. For 1 degree you convert into radian, and then for a meridian for 1 degree is around 111 kilometer, 111 kilometer, and for parallel it is around 96.5 kilometer. So you see, for 1 degree increment the distance we actually covering around 100 kilometer if we is near to the equator within 30 to 30 degree. Okay, so that is how we can calculate the actual length on the earth. Okay, so now this actually whole thing is a GCS system. So if your map, if you try to open a map in GIS, or if you coordinates in degrees, means you are working on a GCS system. Okay, and data or any point in particular map is represented by longitudinal and latitudinal. Now, how actually Earth is represented? I think I have mentioned this thing or these terms in my first PPT also. The whole Earth surface is very irregular. You see, this is Earth surface. So first, the scientists have developed a geoid. A geoid nothing but a surface of constant gravitational potential, that is called GIS. Here your G value is constant. Okay, this is your geoid. Once the GIS is developed, then we take the measurement, physical measurement on the earth, and we interpolate that data and we convert, we make a hypothetical model of the earth. That is mathematical model is called ellipsoid. So that is called data. Okay, currently we are using WGS-84. So this is your earth model, ellipsoid. Okay, now if you are taking a point, latitude and longitude is nothing but you are taking these angle on ellipsoid. Please remember. So ellipsoid is to represent your XY coordinate. Okay, but Z value is always taken from geoid, means it's taken from this geoid. So you should keep this in your mind. Okay, this latitude and longitudinal defined by using ellipsoid, and ellipse rotate about an axis, whereas elevation Z is defined using geoid, a surface of constant gravitational potential. We say MSL. Okay, and the observation made on the geoid are transferred to a hypothetical regular geometric reference system, that is called ellipsoid, for the mathematical computation of the geodetic data reduction, also called geodetic datum or map datum. And the accuracy of such computation and map is directly affected by the suitability of the datum used. So that is very important. First, you have to select the proper datum of your observations or your map. Once you have selected proper datum, then using suitable projection, you represent data in a GIS map. So that is whole concept behind GIS. You have a geoid, it is converted into ellipsoid, and then using different projection system, cylindrical, conical, and projection, you have a GIS map. Okay, so this is the main principle behind the GIS map, how it is converted from a ellipsoid surface to a rectangular coordinate. Now what is cylindrical, conical and azimuthal projection system is nothing but, if you see map projection, what is cylindrical means, suppose you take a transparent globe and in that transparent globe you put a bulb, okay, and you cover this transparent globe by a world map, that should be opaque, okay. So if you illuminate this bulb, the shadow of that, shadow of this map will taken on a cylinder which is wrapped around this globe, okay. So suppose you outline the shadows or you make the shadows, and then you have taken whole map shadow in the cylindrical, and then you cut it and you flatten it out. That map which is now is in this flat surface, it is called cylindrical map projection. This actually the way of describing, in GIS it's used different mathematical equations to make the flat surface map, okay. And this type of projection is called cylindrical map projection. Conical projection, if we take any cone, okay, instead of cylindrical, and that projection of the whole map on a cone and then cut it out and flatten out like this, then the world map which is represented by this is called conical projection, okay. This is called conical projection, okay. This is also a particular set of equation we actually using in GIS, and we can have this type of projection also. And if we use a plane surface like this and we take a projection like in this direction like this, then we will get azimuthal projection, okay. So this is just to represent how actually the conical projection and how it is cylindrical, conical and planar. Now if you see, if you try to see the map from a spherical or a ellipsoid to a flat surface, definitely there will be some error, okay. Means feature will be distorted in this particular process. In case of cylindrical, you see the feature near to the equator have less distortion, whereas feature away from the equator will have more distortion. So this type of projection, cylindrical, we will use for measurement of the things or a feature which is near to the equator. Then conical or cylindrical projection system must be used. For conical, we can use this particular projection system. If suppose my cone is touching this parallel, then the data or any feature around this parallel will be more accurate than the other parallels. But the orientation of this cone can be changed, and we can define different conical projection for different location. So if your data is near to polar side or near to the polar, then we can use conical projection system, okay. And this planar is just generally it is used for giving directions. Means if you don't want to distort the directions, means for suppose in navigation system also, and for aviation generally this map is used, because here your direction is actually conserved, okay. So please remember this thing, that currently we use cylindrical, conical or planar projection system to represent a GIS map, and it is impossible to have a same scale everywhere and the pixel size to be perfectly constant and preserve certain property that depend upon the type of projection you are using. So these things you should keep in mind that all map projection distort features. First thing you should know. What is conformal and orthomorphic projections? It's preserve the local shape, means it retain the property of maintaining correct angular correspondence. The shape of that particular object or a particular feature, it's retained, it preserved in the map. So they are commonly used for navigation and meteorological tasks. And the example of this type of projection system is called conformal and orthomorphic, and UTM and LCC is two type of projections we generally use. So in that projection system, your shape is written, means your area, or maybe some error will be there, but your area is calculated here actually. Then another projection system is equal area projection system, and in this type of projection system, your area remain preserved. Okay, your area will preserve, means if you use this projection system and if you want to calculate the area, your area will come around 99.9% accurate. Okay, and this is called equal area projection system. Now if you want to calculate the length, there is another projection system, that is equidistance projection system, which preserves the distance between two certain points. Okay, so this type of projection generally use radio and seismic mapping and for navigation also. And that last one is assumes the two directions. It's give the two direction along the great circle. So these are the projections: equal area, equidistance, two directions, conformal. Okay, these are the four type of projection system. But these also, there is a thousands of projection system. Means if I will go back now, you see this is conical. If I change the orientation of cone, my projection system will change. So like this, if you change the orientation of the cone or cylinder or this plane, you will get thousands of projection system. And which projection system you use, that should depend upon your study area, where actually your area lying on the earth, and you can use appropriate projection system which is generally or is designed for that particular area. So it is usually impossible to preserve all the characteristics at the same time in a map projection. A map projection is a compromise that distorts all the property of area, distance and angular conformity within some acceptable limit. You need to use a map projection that provides the best characteristics of your analysis. For example, if you need to measure distance of your map, you should try to use map projection for your data that provide high accuracy of distance. Okay, similarly, if you want to calculate the area, then you should use equal area projection. So which projection should be used? That actually come in when you use QGIS or ArcGIS and you do different type of work, then you get to know which type of projection should use. But most probably for beginners, we use or we prefer UTM projection or LCC projection. Okay, I will tell you what is UTM projection, and datum we use generally WGS-84. Just keep this in mind. Right now you have to keep this in mind that datum we will use WGS-84, and for projection we will use either UTM or LCC projection. Okay. Now what is UTM? UTM is nothing but it's a universal transverse markers. UTM, in actually the whole earth is divided into the 60 strips. You will see 60 strips. Okay, and each strip have a different mathematical formula. Means for this particular strip, if you try to convert your data from degree to meter or degree to feet, then you have to use a particular strip which covering your study area. Okay, for India, UTM zone is starting from 42, 43, 44, 45, 46. For okay, suppose Currently we are using a project which is lying in Telangana, and I think 44 zone is covering my area. Okay, so we should use UTM 44. Another thing is you have to tell whether that data is northern hemisphere or southern hemisphere. So because our India is a northern hemisphere, so we should use UTM 44N. If your data lie, or if your study area lie on Maharashtra region, Kerala, Karnataka, or some part of Rajasthan, then you should use UTM zone 43. For Gujarat, we can use UTM 42. Okay. For Bihar, UTM 45. For Northeast, we can use UTM 46N. So that is how we can select the projection system. Okay. So summary, to prepare a map, the Earth is first reduced to a globe and then projected onto a flat surface using different projection system. Generally, three type of projection system we use: conical, cylindrical, or azimuthal. So a projection system which is defined in a GIS is first it have a datum, then which type of projection, and you also define the set of projection parameters. Parameters nothing but you have to define the extent, from which extent to another or your area line. Okay, so these generally 6 type of parameters is there. Okay, you can learn this projection parameter from Google Earth. But right now in this training, best only thing you have to know that if you want to define a particular projection system, first you have to define the datum and which projection system, and that projection system depend upon the your study area on the Earth. Okay, so this is all behind the projection system in GIS. Okay, now I will stop. Okay, this thing also I think you should note. There are hundreds of different projections available worldwide. Each try to portray a certain portion of the Earth's surface as faithfully as possible on a flat piece of paper. In reality, the choice of which projection to use will often be made by you. Most countries have commonly used projections, and when data is exchanged, people will follow the national trend. In our India, the National Space Framework for India used datum as a WGCT4 with the LCC projection, and it is recommended by NNRMS standards. So India generally use LCC projection and WGCT. But for our study or our this training, we will use UTM. And how we can convert data from one reference to the other system, I will tell you in my hands-on session. So this is the end of slide, and then now we will switch over to our QGIS session. Okay. So why actually I have told you about the projection system, because if you want to convert data from one reference to another system, first you should know what is your current projection system, and that current projection system is defined by this EPSG. This particular you will see if you open it. Currently I am using EPSG 7756. Now I want to convert the data from this reference system to another reference system. The steps are: first select that particular layer, export, save feature as, format should be save file, give the path of the new file, suppose it is my reservoir. Okay, and the target CRS means this is the required project system you want actually. So we will use UTM. We'll use UTM 44 North. So this is our target CRS. Select it and just press OK. New layer is created in the new project system. That is how we can convert the data from one project system to another project system. You can see this. If you see the property, this is your original layer. Here projection is WCS-84 Andhra Pradesh. It is LCC projection actually. And your new layer, what you have created, it is actually UTM 44N project system. Okay, so this is how actually the projection. WCS-84 is your data slash, after that it is your projected projection UTM Zone 44. It's a cylindrical projection. Okay, so I hope that you learned how you can convert data from one projection system to another. So I think I can remove this layer because this was created only to show you how we can convert one reference system to another reference system. Okay, we can remove this layer. Now, before calculating the area and length, you should remember that if your data is created using GCS system, means if your data is created using any satellite image or a topo sheet which actually use degrees to represent the features or data, then you have to convert that vector layer from WCS-84 to a particular projection system, UTM or LCC, because you want to convert data from degrees to meter or feet. Okay, so I told you that how we can convert your data from one project system to another system. Now this reservoir layer is currently using LCC projection, so my data is right now is a projected coordinate system, which is a PCS system. Okay, so again, you please keep in mind, if you trying to calculate area or length, your data should be in a PCS system, projected coordinate system. It should be in degree, not in degree, it should be in meters feet. So you see currently your coordinate is showing in meters. If you see, there is no degrees there. Okay, so that is means we are actually working on PCS system. So how to calculate the area? Now this reservoir layer is in a PCS system, and if I want to convert I want to calculate the area, then what you do, first you open the attribute table and then you create a column. You should create a new column. So you toggle editing mode, means you want to edit your layer. You create a new column by using this new field. Now it will ask your column name. Now I can say area 2, that is my column name. Now what type of data that column will contain, whether it will be a text or whole number or a decimal number. So it's a decimal number, and I want the default is actually it will calculate in meter square. So I think the area in the range of 8 or 9 digit. So you give here 10 digit, length is 10 digit, and precision is 2. Okay, and you give okay. Now new field has been created, And now how to calculate area? You use this open field calculator. Open this, then update existing field. Which field you want to, or which column you want to update, you specify it from here, area 2. Okay, this is the column you want to update, and then go the variables and go to the geometry. In geometry you will find $sign area. Double click it, that area should come in this window. It will come after double click it. Okay, so $sign area, and then press OK. So you will see area is calculated now. So it calculates the area of whole features in the layer. If you have suppose 100 of polygons, then it will calculate area of all 100 features. Okay, now you want to calculate the area in kilometer square. Same step you can follow. Create new column, area kilometer 2. Your name should not be, means it should not be matched with this already existing name. It should be different. If you try to give same name, it will give error. So I think area kilometer 2 is already exist. So what you do, you just put underscore here. Okay, put underscore here, and then decimal. I think you can give 5 and 2 here. Okay, then open update existing field, area kilometer 2. I want to update this particular field. Go to the geometry. Same steps you have to follow. Only thing you have to do, you have to divide it by 10 lakhs to convert meter square into kilometer square. Okay, you have to do this thing in this window. Okay, you give proper expression. Once you have given the expression, press OK. See, now your area in kilometer square. Okay, that is how you can calculate the area. Similarly, you can also calculate the length of a length feature. Now this is the polygon, the reservoir contains the polygon feature, so you only calculate the area. But for canal or road or dam, because these features are line features, you can calculate the length for these layers, and for length you have to use this variable. In geometry you have to use $sign length. This should be used. Okay, so steps will be same. You click first, select that layer, then you have to enable the editing mode. Okay, using this tool. Once you enable the editing mode, see you see the pencil here. The pencil shows that your layer is now in editing mode. Okay, this pencil you see. Now third step is you have to create a new field, new column, assign particular data type you want to store in that column. Then you have to use this open field calculator. Check this update existing field, select the proper column you want to update, and give proper variable. The variable should come here. Okay, and then press finally OK. So these are the steps to calculate the area and length. Okay, I think now you know how we can calculate an area and length. So that was all the topic I want to cover in this session. In next session we will learn how we can export our map into a PDF format, how we can introduce scale or legend, and then north arrow. Okay, after that, once you know how to create a basic map, then we'll learn about little bit about how we can create a vector data using a digitization process. So next session will be to create data by digitization process and also how to export our map in a PDF format. For that, now the session I will stop. Thank you very much.